and the kind of production. And today I wanted to talk about some strategies for detecting the low energy astrophysical or partly astrophysical neutrino fluxes. And first, I will be talking about how we can detect the sub-100 MeV component of the atmospheric neutrino flux. And then in the second part, I will move towards how we can make some steps towards detecting the non-electron part of the diffuse supernova neutrino background. Okay, so let me start by just showing you the grand unified neutrino spectrum, where you can see the different neutrinos from different more or less steady state sources. We have here reactors which might be turned off and on, but the rest should be more steady in time and we can detect them. We can see here that it spans many orders of magnitude, and we already did some progress towards measuring parts of this neutrino spectrum. So we measured the solar atmospheric neutrinos, reactor neutrinos. We also seen the astrophysical high energy neutrinos. But as you can see here, there are still some gaps. There is, of course, the gap on the lower energy part, which is very challenging to detect. But we also have the gap around 10 to 100 MeV, where it's especially where the DSMB and atmospheric neutrinos are. So why we are so interested in detecting those neutrino fluxes? Well, with the higher energy atmospheric neutrinos and solar neutrinos, we found out that neutrinos do oscillate and they do have mass. So they are only standard model particles with proven beyond the standard model physics. But there is more to that. So here we can see how the atmospheric neutrino flux evolves as a function of energy. And you can see the data points coming from superconductivity or ice cube. But as you can see here, the precision is pretty good at intermediate energies. It gets worse towards very high energies, but there is no measurement below 100 MeV. And why we are so focused on measuring those parts of the spectrum? Well, so the first reason is that while we made already pretty good progress with the neutrino physics, we know that neutrinos are oscillating, we know that the mixing angles are pretty large. There's still some questions to be answered, like what is the nature of the neutrinos? Are they Dirac or Majorana particles? What's their absolute masses? With the oscillation experiments, we only measure the mass square differences. Also, is there a CP violation in neutrino sector? And finally, we want to make kind of robust picture of this astrophysical grand unified neutrino flux. So it would be good to measure the slow fluxes. And you can see the evolution of the precision in neutrino physics on the plot on the right-hand side. And now we are moving towards even higher precision experiments, because the Dune, Juno, and other large experiments will become online. So we want to really use all the possible resources as like theorists or phenomenologists to get as much as possible from this data. And to get to that point, we want a really variety of approaches to get this super sensitivity. But that is not the only reason. The atmospheric neutrino fluxes, especially the low energy ones, are backgrounds, especially for the direct dark matter detection experiments. They compose the so-called neutrino fog. So as we have more and more volumes in those dark matter detectors, they will start to see neutrino post recoils on the nuclei. And depending how well we know the background, which is the atmospheric neutrino, that is part of it, we can make different predictions what can be the cross-section or what is the limit for the cross-section of the dark matter. So this one thing, the way we want to measure it is mitigating uncertainties in the discovered potential of dark matter experiments. And another thing is the atmospheric neutrinos are also background for the diffuse supernova neutrino background. And why I'm excited about the diffuse supernova neutrino background is because this flags actually carries information about the old past supernovae. But in order to detect it, we need to deal with some of the backgrounds. And while Super-K now is making a very big effort to detect it, still we would want to get better knowledge of the atmospheric neutrino background. So here you can see different predictions for the SNB as a function of neutrino energy and the regions where different backgrounds will affect the flux. So I want to now focus in the third part of my talk on the paper that was done together with John Deacon, where we try to use the distinctive nuclear channels in carbon to detect the low energy atmospheric neutrino flux. Okay, so if we look at the atmospheric neutrinos, the low energy part comes mostly from the ion and muon decays from those chains. And here we can see the flux as a function of energy for the sum of mu and anti-mu and electron and anti-electron neutrinos. But because now we know that neutrinos have masses, when we measure the flux at the Earth, it's not the same as it was created in our atmosphere. So we need to take into account the oscillations. And if we look into detectors which don't really have the best reconstruction of the direction, or we focus on just events from all the directions, it turns out that the non-oscillated ratio, which is 1 to 0 in all neutrinos, turns into 1 to 1 to 1 because of very almost maximal mixing angle between mu and tau sector. And then only once that happens, the smaller the diameter electron neutrinos doesn't really change that oscillation favor ratio. So here we can see as the fraction changes as function of neutrino energy, and we can see that low energy neutrinos, all of them will oscillate, but as we go to higher energies, which means also that we need longer baselines for them to see the oscillations, we can see that this ratio will deviate more from 1. But as the peak of this energy-weighted flux is around 200 MeV, we can basically approximate that we have 1 to 1 to 1 for most part of our detected spectrum. Then the channels that we focused, the first of them was to detect the all flavors of neutrinos, so kind of get the normalization of the atmospheric neutrino flux. And this is the neutral current channel with carbon, which produces the 15.11 MeV excited state, and that state excited by emission of monoenergetic gamma ray. And if we can look at the sketch here, if we have backgrounds which are relatively constant or more or less maybe even parallel or something, we can also be easily distinguish this very narrow line with if we have detectors with good energy resolution. So Juno should have good energy resolution, which will hopefully help us to see that signal. Then next channel is for the electron neutrinos and antineutrinos. So here now we have also nuclear channels that lead to the excitation to the ground state of nitrogen and boron. And then once this the produced nucleus will decay by beta decay, it will give us signal in electrons. And by measuring the prompt signal, so the electron from the prompt charge per interaction and then the delayed beta decay, we can correlate those events and kind of be sure that we are measuring actually electron neutrino. And additionally, if we can distinguish between the times of the beta decays of those products, so N12 and B12, then we can know if this was neutrino and antineutrino reaction, or if the detectors can distinguish between the positrons versus electrons, then there is a potential to have measurements of neutrinos and antineutrinos at these low energies. And we can finally go even to the mu, not mu-e, which kind of produces the same signal as before. But now, because we have muons, these muons will also decay, and we have triple coincidence signal. So here we have distinction between the electron muon channel, and then the distinction between the anti-mu and mu is similar as for mu-e and anti-mu. Okay. So all these channels were also looked at not only for the atmospheric neutrinos that we're looking at now, but also for the supernova detection, because the energies of neutrinos from supernovae are kind of tens of MeV, which is right to get those signals, at least for the electron and neutral current channel. And as I already mentioned, we were focusing on the Juno detector because it's gonna be, and it's under construction, a very big liquid scintillator detector, which should have very good energy resolution and spatial resolution. So this would help us to distinguish those channels because we can locate the events, and also we can resolve this very sharp feature.
Can we do that also at Berkeley?
I think in principle, yes, but I think Berkley might be too small. Like it was too small to get the events. We get like, I think 16-ish events after 10 or 5 years, 5 years, depending on the energy efficiency and the efficiency. So I don't think Berkeley could see atmospheric neutrinos.
Using this line, so
Yeah.
16.
Yeah. But in principle, I think yes, but I think Berkeley had a bit worse energy resolution.
That's why I was
Okay.
wondering whether you were not doing it because of it.
I think the main thing would be probably the exposure if this was small detectors.
You guys have a question. You had like a continuum background, and then you had like a starting on the line. Was that continuum background? Was that atmosphere between a continuum background, or was that just something you could?
That is a cartoon. I will show the real more background, the atmospheric and solar part, and kind of say why we think we can neglect some of them a bit later. But there are more questions. No? Yeah, so I now will go into why the low backgrounds and how we model the cross section. Yes, so first we have the cross section. We did the elementary particle treatment, which works for low energies. And the cross sections agree with data pretty well, reasonably well, if we go from the left-hand side to the right-hand side. That higher energies, there might be changes in those cross sections if we use better calculations like shell model calculations or the mean random phase approximations or other type of calculations. But as we've seen in the literature, our cross sections differ by 5 to 40% between those. But this is the step where if people want to improve, that would be great, because we've seen that we can see some events, not unreasonably small number, but that's the part that can get improved. So there is the work to do. Now agrees pretty well, but there can be work done here in this part.
Bigger calculation gives the bigger cross section or the smaller section?
That depends on exactly what they do in those calculations. Sometimes bigger, sometimes smaller.
It's kind of still more than
Yeah, and then
so she's just using those results.
right, and then depending on the choosing from other than would it be possible to investigate some event that's not working? Even the person.
Well, 5 to 40%. So he's
Yeah.
obtained so 40% of that. So that's it's still within the.
Yeah.
So because Carmen is using that, so
Yeah.
Carmen has seen
Yeah.
the neutral current.
Yeah.
That's the basic thing. And then you keep your more results.
Yeah, but Carmen basically saw just one energy. They saw also average energy, but if you want to have energy, the kind of cross section, that was just single energy. Yes. So with those cross sections that they shown, we then calculate the number of events in the detector using the energy resolution and efficiencies and the fiducial volume for the Juno to take care of some of the backgrounds. And here on the right hand side, you can see the number of events as a function of detected energy for the neutral current channel. So this green line is the signal from all flavor of neutrinos exciting the carbon-12 to the excited state, and then with the excited giving us the line, which is now spread out because of the energy resolution. So for the backgrounds, the biggest background would be the atmospheric neutrinos scattering on protons, because those are single events, either the bound in the nucleus protons or the single proton. But we say, relying on the Juno papers, that this can be discriminated based that those are protons, so they lose energy differently in the medium than the gamma rays should lose, so we can differentiate between those. And then we also have the tail of the solar neutrinos, the HEP and the iridium one. So those can affect this measurement if the energy resolution is much worse, but if it's what they expect to be, probably we don't have to worry about electron scattering. And yes, with 85 kiloton exposure, we get 25% uncertainty up to 40, depending what how many years Juno would be running. What will be the efficiency of Juno and how much they need to cut the signal in order to get the cuts for the muons in the detector. And for the charge current channels, you can see the prompt signal on the left-hand side of the lower panels for the electron neutrinos, antineutrinos, and electron muon neutrinos and muon antineutrinos. And those we are doing essentially background free, because we want coincident detection within small volume of the detector and also a relatively small time. So I think for the 85 kilodalton exposure, we got that the accidental coincidence rate was around 10 to the minus 4. So for the triple coincidence rate, this should be even smaller.
So maybe I missed so okay. So irreducible background, the solar and this, you know, what's the other final state
Of which one? The solar?
Irreducible, NC channel.
The NC channel, the final state is gamma, the single monoenergetic gamma.
Only gamma.
Yes.
So that's the other irreducible background. Then so I guess the Juno is just measuring the energy deposit, right?
Yeah.
Then what if like electrons, accidentally give like a similar energy, like 15 MeV each energy deposit, but still you don't know whether that is coming from electron or the photons.
From the solar neutrino scattering on electrons?
Yeah, so this is a scintillator, right?
Yes. Yes.
The scintillation like happens. I mean, you're not measuring the single 15 MeV the photon, or do you just measure the one the PMT measuring just 15 MeV photon? Right?
I think you measure the positive energy and you construct the vertex.
So then the even electrons will give you the 15 MeV energy deposit, and then you don't know whether that is coming from photon or the electron.
But you mean like electron exciting the carbon, or just neutrinos from sun scattering on electrons?
So now I'm actually thinking about like really sort of the reducible electrons. It's giving rise to the electrons. I mean, that's just one example. But in an accident, I mean, it's a continuum spectrum, but it's an accident that it gives you the 15 MeV deposit. Probably, I guess you're looking at a very narrow window, right?
Yeah, but where would they come from?
You've done some kind of background modeling, right?
Yeah, so
that's what the spectrum is.
yeah, so the backgrounds are
Exponentially going down.
the exponentially going down is solar neutrinos scattering on electrons in Juno. There are also radioactive backgrounds, but at lower energies.
That's like below 2.6.
There are also higher, but yeah.
Okay, so yeah, okay, so we can talk about it.
But maybe there's something like I didn't take into account yet.
But to what, like you need to produce a line. Like you were saying accidentally you produce a line.
No, when line is positive,
No,
line is positive.
but he's thinking about taking the line.
No, but he's thinking if your flat background is high, then.
But that's it, you can do side band to correct the flat background.
I think like, so event by event, like, you can't distinguish.
No, no,
between
right,
them,
right. So that-
that's.
even if
but-
I-
but- yeah.
Yeah, even if I know the background subtraction, the side analysis, still I, have, the background events there in that, narrow window. And then on top of that, the signal is there, still. This much is my signal and this much is the still.
Yeah, but you know, like from the flat background, you know exactly what to expect, so you can subtract.
Yeah, but I can't, the fully subtract the background. Let's think about, the HEPEC search, right? So bipolar channel. So narrow window, but this much in the background is still there, and that's over E.
So I don't know, like if you do the sideband, I can, if I have the infinite accuracy to determine the background, I can make the background easy. Oh, yeah, because I can cancel the, because I don't see a line, that's my point. If you don't see a line, you can get rid of everything. Depending on how well you measure on the, how well you measure the background everything else.
But I mean, when I remember the HEPEC search, the background is not zero. It's
No, but the Higgs search is not the line given by a nucleus, which is no. Higgs search two photon can be can count anywhere. Higgs mass is variable. But here this nucleus you know.
But here you're not claiming it's backward free, you're saying essentially that.
Yes.
So it's not completely.
Yeah.
So those are just scale, right?
Yeah.
The scale of the line, so that,
Mhm. So basically in this energy window, we kind of say that the really irreducible background would be this solar neutrino scattering of electrons.
Okay, so let me ask this question. Suppose you observe, the 15 MeV energy deposit. Then you can say, okay, so this is either from, so your signal for just, the single line, the background event. And no other, the fake one. Let's say some continuous background, but accidentally energy deposited at 15 MeV. And then your detector just measuring with 15 MeV. But still you can say, okay, so there's no chance that this is coming from like a fake signal.
I mean, but you can calculate based on your prediction what is the probability that is coming from the background versus the signal, and then at least what I imagine, you wait for some time to get this many events, and then you kind of know if this is background or signal.
Also, then, so based on your knowledge and the simulation, this much,
Yeah.
this fraction of the events are background, and then you just really literally cut away those.
I mean, here I don't say that I cut away for this uncertainty. Like I do very simple high square, and I take whatever background I have to say that that would be my uncertainty, depending if I use the signal from scattering on protons or not.
Okay, so then that is translated to your uncertainty.
Yes.
Okay.
Okay, sorry, I'm sorry it wasn't
No,
clear.
So Carmen did the same.
Yeah, but yes. But yeah, we need to.
but actually, now I'm seeing point about this, is like the atmospheric background, the purplish band, like correlated with your signal band, because like, what's, it's a thing. What?
Yes,
So, okay.
yes,
Yeah.
yes, that's also true. That's why it's uncertain too. Yeah, okay, so this would be my conclusions for the first part, that we are moving to a very high precision neutrino physics right now, and we want all hands on deck, all available detectors, all available channels to get as much information as we can. And potentially we would have with these channels a first detection for the charge current cross sections for anti-neutrinos, because Carmen and the SND didn't have high enough energies because they were using pion decay at rest or in flight, but then they only produce the muon neutrinos, not muon anti-neutrinos, because it's hard to get the muon anti-neutrinos. I forget now why, but I remember later. I'm sorry. And these channels give us clean observables And we will have a better knowledge on what is the background for the DSMB and dark matter searches. So any more questions for this part? I think there are ion captures on nuclei for the negative ions, and that's why it's harder. Okay. If not, then I'll move on to the second part, which is the towards detection of the diffuse supernova neutrino background in all flavors. And I will very briefly discuss what are the supernovae that produce neutrinos and why people are excited about this, or why I'm excited about this. So when we have stars which are very massive, like approximately about 10 or 8 solar masses, as they evolve throughout the different phases of fuel burning, they tend to form these onion shell-like structures with the heavier elements being inside and the lighter surrounding it. So when this very dense core grows to a substantial size, basically the Chandrasekhar mass, the electron pressure can no longer support it against the gravity. It starts collapsing and we can get supernova explosion, which is visible also in the photons, but also in neutrinos as they are 99% of the burning energy. They very easily escape. Or we can get direct collapse to a black hole, and we will probably only see neutrinos, maybe some visible light, potentially also gravitational waves. But in this process, we get 10 to the 58 neutrinos. So that's a lot of neutrinos, which can give us a lot of information. Oops. Yeah, this lady basically told us that stars are balls of gas. So that's why we know we have balls of gas in the sky. Okay, so why core-collapse supernovae are good physics problem? So from those neutrinos, we can get access to very extreme environments, hot, dense, and also environments where the neutrino interaction can be important, but also those neutrinos already travel over very, very long baselines. So this is something we cannot really probe at the Earth here. And while we already detected neutrinos from the supernovae 9878, we only seen a handful of events and in electron antineutrinos. So we don't really have as much information as we would like to. But with these upcoming detectors and existing ones, we will get a much better picture because it won't be only electron antineutrinos, but all the other flavors, and with much better statistics. So here is the list of some things that we can learn about supernovae and about some of the particle physics with this variety of detectors and next galactic supernova. What is the explosion mechanism exactly doing? We think that it is the neutrino heating that energizes the Stall shock and launches the explosion, but it doesn't happen for very massive stars and it doesn't always produce very high explosion energy. So some things might be there missing. We can also maybe get some information about the nucleosynthesis that is happening in those stars, or what type of compact object formation is happening. If we form neutron star black hole, how does that work? Or if we form some other object that possibly is made maybe not of varying degrees of freedom. And finally, we will get better insight of what is happening with the neutrino evolution in this dense media with the neutrino-neutrino interaction. And maybe some hints, or if not, we can possibly get better constraints on the non-standard physics. So this is all exciting, but the single galactic supernova are rare. Like last one happened a little over 36 years ago, and we can get precise information with what is the detector, but only about single star. So it will give us a lot of information, but there may be some differences that we won't be able to observe. So that's why we want to measure as many as possible supernovae, and the price we have to pay for that is unfortunately going to larger distances, which means that we will have lower fluxes and we would need to have good detectors to distinguish this signal between the backgrounds. And that is the diffuse supernova neutrino background. So the isotropic and stationary flux coming from the supernovae that exploded in all the observable universe. And here you can see how to calculate it. And it basically tells us this equation that the DSMB should be sensitive to the cosmological supernovae rate. What is the flux from single supernovae looks like, the redshift evolution, and also favor evolution that is happening inside the star. But one of the also more important things is not exactly mass equation rates in black hole supernovae, but the flux from black hole forming versus neutron star forming supernovae. Because we think that the black hole forming tend to have bigger, hotter cores, so they will emit more energetic fluxes and easier to detect. But all those ingredients can be, in principle, distinguished with DSMB, but they're gonna be buried inside. So we need to do some disentangling.
What do you mean by more energetic fluxes? Do you mean more flux or more energetic?
More energetic neutrinos. Yeah, sorry. Yes, so I will briefly go through some of the astrophysical uncertainties, where the first would be this fractional backflowing supernovae, which is still rather unknown parameter. And here you can see different theoretical models of different masses of supernovae. And depending on the set of initial conditions and simulations, they either form neutron stars or black holes, and the fraction weight, which is weighted by the initial mass function, can range from 9-ish to 41%. And those numbers also agree with the observations of non-explosions of the red giants. And this is important, as I said, because then from this black hole forming supernovae, we form more high energy neutrinos than in cases of the neutron star forming, because we have bigger, hotter core. So this is important for DSMB, because if you look here at the different line styles, you can see that as we increase the fractional backbone progenitors, the high energy tail of the DSMB is increasing. And that's important because the energy window of detection is between 10-ish to 30 MeV. So we want as many neutrinos in that window as possible to make easier detection. Another uncertainty is cosmological supernova rate, which will mostly affect the normalization. There are also different shapes, but we will be mostly sensitive to the redshift, maybe around 2, because at higher redshifts, the neutrinos are redshifted, so they have lower energies and it's harder to detect them. And we did some study to try to see if we can actually constrain the fractional backbone progenitors and cosmological supernova rate using the detection of DSMB in 20 years of HEPEC in Juno and June. And we get the 1 sigma uncertainties ranging between 50 to 20% depending on the conversion scenario in our progenitor and also which detectors we have. So here June is very good at lowering the uncertainties because it gives us different detection channel. The HEPEC and Juno are anti-neutrinos, or June will be the neutrino channel. And the same happens for the cosmological supernova rate. We also can try to narrow down its uncertainty with the DSMB detection, which is of order of what is the current observational activity. But with if there are in observatory, this might might get lower with the electromagnetic observations. We have more uncertainties there because, as I said, there's also initial mass function, so the distribution of stars as they are born. And some surveys are finding that at higher redshift, the initial mass function is more top heavy, meaning there are more massive stars than from the single vanilla salpeter form. And that would change the core collapse supernova rate and then also translate to the DSMB through core collapse supernova rate, but also the fractional backbone progenitors. And we looked at that a little bit, and assuming that all the other uncertainties can be just put into the one single normalization uncertainty, with the detection of DSMB in HEPEC for 10 years, we can get 1 sigma sensitivity to that. But this is pretty low sensitivity. So we want better observation also from electromagnetic spectrum to narrow down what is happening with the core collapse supernova rate. More things. we know that stars now, we now know that stars are mostly residing in binaries. If this is happening, we can get mass transfer or mergers. And what that does is change the number of progenitors that are actually exploding or going into core collapse supernovae. So that will change if we have, for example, 5 solar mass star, which then transfers some mass from other star, then it turns out that this star can explode and enhance the number of core collapse supernovae producing neutrinos. With very simple thing. There is additional issues with the rotation, but I'm not going to go into that. But basically, inclusion of the binary interactions increases the DSMB, which is kind of good for us because it might mean that it's easier to detect. But it is another astrophysical uncertainty that needs to be taken into account if you do any non-standard physics in the DSMB. I have any questions now? Okay. Then I will move to the DSM scenarios that can affect the DSMB. And first of them can be the neutrino decay. So we know that neutrinos have masses. We know that different mass states don't have the same masses. So neutrinos should decay. But because the mass differences are very small, the time for them to decay would be longer than the observable time that we have. So we cannot really see that. But if neutrinos are coupling some other beyond the standard model mediator, which they might as well, because they are the only particles which have beyond the standard model of physics, then they also can decay. And because the DSMB neutrinos travel over very, very long baselines, it means that they have time to decay they have a lot of time to decay. So the detection of DSMB can be used as putting limits on the neutrino lifetime. And one of the best limits, best direct limits, the C and B can put some limits, but this is not for the detection of neutrinos. And then CUB can be even better, but we are pretty far from that yet. So here you can see how that can change the signal. On the left-hand side, you have the event rate in hyperchemical without the neutrino decay, and then with neutrino decay. So depending on the exact scenario that you have, you can get increase or decrease of the number of events. Here it is increase because we are turning more, we are making more light mass eigenstates, so more millibar neutrinos are bigger. And this can probe the lifetimes versus mass around 10 to the 9. So as you saw on the previous plot, pretty long. Then we can also have mediators that are kind of special in a way that they will produce some dips in the DSMB. So there has been studies by looking at DSMB neutrinos interacting with the CUB neutrinos, which if you have the right mass of the mediator, so the resonance energy, the dip energy that you see is equal to twice the mass of the mediator times the mass of the mediator squared divided by 2 times mass of the neutrino, you will see the dip. And this dip is actually a very nice feature because all the astrophysical uncertainties I talked about before are mostly changing the spectrum in a smooth way, not really like some big dip in the half of the spectrum. So this is kind of resistant to those uncertainties and potentially one scenario that can be probed very well. So people also, yeah.
This theta is
This theta?
Yeah, this theta is between what level and S, or is it like a universal?
Yeah. So I talk about DSMB neutrinos with the cosmic ray neutrinos. This is not what is on the plot. DSMB with dark matter just with the single genome mixing. This is not what is on the plot. What is on the plot is freshly from the archive today, yesterday night. Paper that we looked at the secret neutrino interactions for sterile neutrinos. So I have background, the relic sterile neutrino background created in the early universe. so M4 mostly sterile, and then DSMB neutrinos, the sterile part of the light mass eigenstate is interacting with the sterile part of the high mass eigenstate and creates a dip. So I'm constraining both the coupling, the self-coupling between sterile neutrinos and the mixing angle between the active and sterile. And here I'm assuming the same mixing angle for all the flavors. I don't know if those make sense. The dark matter is the sterile neutrinos with KeV masses. The sterile part of that interacts with the sterile part of the light mass eigenstate in the DSMB. And that's why I have dips. And the nice point of this paper is that part of this parameter space that HEPEC can probe is also probable by Tristan, which would be like the Earth terrestrial experiment, which people tend to believe more than some astro stuff, but it's some people, not all. So if we see signal in Tristan in this region, and we also see signal in DSMB with dips, that can be hint for the sterile neutrino dark matter. But
Did you have 100% for that?
yes, this is 100% depending on what is the resonance energy and the basically temperature of the neutrinos emitted from the supernovae. So there are constraints here. So if you have a model that can evade those constraints, that's a great way to probe it. If you don't have a model that can evade those constraints, oh, yeah. There can be also stuff happening inside a supernovae that changes the active neutrino fluxes that are going out of supernovae. So we can also have changes there. I'm not gonna talk about it, but one of the stuff I also work on was KeV inside a supernovae, and that should cause a lot of changes. And no standard mediators. But in the purpose of the time, I will try to speed up. Okay. Any more questions about the previous part? I'm sorry. If not, then here we can see what are the current limits on the Milli bar from the super K. This is the part that is without the gadolinium, but the gadolinium limits are also similar. And it's basically around 3 to 2.7 in those units, which is the integration of the DSMB above neutrino energy 17.3 MeV. And those limits, as you can see, are only a factor of few above the theoretical predictions. So that's why super K and also I am excited that maybe there will be detection of DSMB soonish. The limits for the electron flavors are kind of order of magnitude worse from snow, and possibly it is detectable by the dune, depending how well they do with the spallation backgrounds. And if they do well, maybe they should see DSMB. But what about the X flavors? So the mu and tau flavors, which for supernovae are just X because we don't have high enough energies to produce a lot of those neutrinos inside. There, the limits are around 3 orders of magnitude worse than the theoretical predictions. And as we see, there can be a lot of stuff happening, especially in the DSM sector, that if you want to know what's happening, really you want to measure all the different flavors of neutrinos to be sure that there is no new physics hiding somewhere that you didn't measure. So in principle, if we look at this plot, we can see that there is a window where we can detect DSMB in all flavors. This is the sum of their flavors, where DSMB is higher than atmospheric and above the solar background. So why those limits are so bad? This is because we cannot really do charge current for the DSMB neutrinos because they have too low energies. So this limit is from scattering on electrons in super K. And there are other backgrounds there, so that's why the limit is bad. And the idea we had with John and Irene is that maybe we can use sevens, which also we did some time ago, but we did it with some more predictions. And this is good because The cross sections are much higher than the IBD because it's coherently enhanced by the number of neutrons inside the nucleus. They are insensitive, and the coherence is in the right range for DSMB. Another good thing is that we have, and we will have in the future, hopefully, big dark matter detectors, which for my purposes can be as well 7s detectors, because they should see the recoil from electrons, and they already have pretty good background suppression and know what is happening there. They have already pretty good efficiency as well. And as I said, big volume. So we can calculate the scattering rate from DSMB and solar neutrinos atmospheric and see what's going to happen. So on the left-hand side, you can now see the event rate as a function of recoil energy in xenon-based detector. And then the DSMB is under the atmospheric and solar neutrinos. So what happened is, even though high energy neutrinos produce high energy recoils, the highest probability is still producing the low recoil. So basically, atmospheric neutrinos got smeared over the DSMB. So this looks like maybe detection is hard. I think we maybe have a different view on that. I don't know. Yes, but can we put a better limit? So the previous limit was like a factor of 1,000 worse than the predictions. And if we look here, now the event rate includes the efficiency and the energy resolution of those detectors. We see that if we just naively scale the DSMB by a factor of 1,000, it is much higher than the backgrounds. So this tells us that we can improve the limit by 1 or 2 orders of magnitude. And this is what we saw. For the left-hand side, you can see the limit on the X flavor of DSMB as a function of exposure for the xenon-based detectors, and here for the lead-based detectors. We can see that with the current exposures, we get the similar limits are super K in principle. And with the higher volume detectors and longer exposure, for 10 to the 3, we can get to a factor of 10 only from the theoretical limits. With even higher exposures, maybe you can have some detection, as I saw. So this is just, again, naively scaling our DSMB, so changes in the normalization, but we can also change the shape of the spectrum. So here we have the sensitivities for 1 to 1,000 ton-years. And here we have the total energy emitted in single flavor X neutrino DSMB. And here we have the mean energy of those neutrinos. So we are changing the normalization and the shape of the spectrum. And we see similarly that with these high exposures, we can get not that far away from theoretical predictions, but also we can get limits that are also good for the new E flavor, which were 10 times worse than the new E bar flavor. Okay, so why this is not yet detection, or maybe detection if we are lucky enough to have very high volume detectors that work great. This already can improve the limits by quite a lot and bring us closer to see what is the whole picture of the DSMB. Okay, thank you very much.
Okay, so questions for Anna?
We somehow missed the crucial step from when the DSMB was in bug. We could have that window where you could detect it, and then 2 slides later it was maybe one.
Yeah.
Can you say again?
So, like here I can see this window, but I have atmospheric neutrino flux. So the atmospheric neutrino flux is lower at part of the energies, but it's then growing at higher energies and have higher energies neutrinos in it. So when I then use the cross section and the fact that if I look at the differential cross section with higher energy neutrinos, I can cross higher energy recoil, but the highest probability is still to produce low energy recoil. So all those high energy neutrinos from atmospheric neutrinos produce a lot of low energy recoils as well, so much that they can bury the DSMB underneath.
Yeah, it's like falling like a rate for support, I guess.
Yeah,
And that's the, this is the coherent neutrino scattering, right? So they're mostly incoherent, your atmospheric neutrinos.
yeah, it's just mostly passing the neutrinos. Pass.
So like, I'm not even like this out, like where's Super K with their search for DSMB? Like they, seems like for 20 years they've been sort of on the verge of like where they think the signal is, but they haven't conclusively done that.
Yeah,
Sorry, I guess this is where I jumped out.
yeah, this is basically those are the purple ones is the latest limits without the gadolinium, and then the green ones are all the previous one also without the gadolinium. So I think here they added the tagging on protons, a small tagging on protons
In the
possible.
2023 one they did.
In the 2023, they added some tagging on gadolinium, I think, because they went to lower energies, and the results from that was also similar to what is shown here.
But like the exposure for the gadolinium run is not very big yet. Or
It's not very big
so
yet.
that's why they haven't gotten it. That should just be holding out right.
I mean, there is a band of theoretical predictions. You might be very unlucky. I hope not, but yeah.
Actually, on this note, actually, isn't there like measurements of like the supernova rate at the redshift that you could just like, you had some bands that were like cosmological predictions.
Yeah.
And they're just like measurements of the supernova rate at like the redshift. I think these have gotten better, right? Where you can actually just like feel it.
So
Yeah,
I think those are the measurements. Yeah, but I think the Vera Rubin Observatory with the SST survey is supposed to see many more supernovae, but especially low redshifts. So that might improve the uncertainty.
Like for like the super K measurement, you're just like sensitive to like super low redshift, right? Like the very
Yeah, basically from 0 to maximally 2, I would say. 2, maybe 3 a little bit. That depends also on the shape of the spectrum, how many high energy neutrinos you have.
So one thing I missed was like, the black holes neutrino and the diffuse supernovae background neutrinos. How do you differentiate them? We don't know, right? I mean, we'll see something in the detector. We have no idea where they are. Are you looking at, is the trick that you just described, like look at low redshift only so that you exclude a lot of the black holes or what?
The trick is kind of what you see from theoretical modeling, and like we have the data from 1987A, so we have some idea what should be the mean energy and the normalization of the flux, and we think this supernova formed a neutron star. And then we have simulations which show that for black hole forming progenitors, those stars can live, the proto-neutron star can live longer, so it emits those high energy neutrinos for longer. So then if you look at the flux, it is described by effectively higher mean energy. So depending on what you use for your modeling of DSMB, like maybe this like this bit, oops. So like here, I'm just showing bands, but actually those are DSMB. Ideally, you would use just all the masses and predictions for them. And then the predictions show that the flux from neutron star forming stars is different than the black hole star forming stars. The black hole star forming stars are described at higher effective temperature. So it means higher neutrino energy.
Yeah,
And
but I don't, without a directional detector, all I'm going to see is something. I have no
Yeah.
idea where so then
Yeah.
I have to depend on the model.
Yeah.
Yeah, you
Essentially,
have
it's
to
a
do,
model.
yeah. But if you have too many black hole forming supernovae, or if your models for black hole forming supernovae predict very high energy, so if the accretion of the black hole happens on the like 5-second time scale, which is pretty long, then you would get very large amount of high energy neutrinos, and some of that is already excluded. So there are some limits on the theoretical predictions from the DSMB limits from Super K. because otherwise you would have too high of a spectrum. But yes, that depends on the modeling.
Is there any quantum dissipation acting on ESNB when they are propagating?
So they should undergo like the spatial decoherence, quantum dissipation. I'm not sure what you mean by that.
So the like the oscillation, I mean, the oscillation effects are just like, I mean, they're like mass eigenstates.
Yeah,
so
they just
yeah.
separate the mass eigenstates. But also there's a lot of effects inside a supernovae, and the many body effects for the neutrino oscillation. So like if we look at the quantum information science, it's a growing field and many people are working on it, if that is what you're interested, because now we have basically kind of a box that contains a lot of neutrinos, and if we look at them as plane waves, we can build a lot of entanglement that can potentially change how the oscillations are happening and what we would see at the Earth looking at different flavors. There is one in Madison, but it's not very great, but they are working on it.
So any other questions? If not, the last thing is.